Dear viewers, hearty welcome to this Walk the Talk program. We at LPSC would like to give a glimpse of the propulsion, a major domain in rocketry. We are fortunate to have with us Dr. V. Narayanan, an eminent technologist who has 38 years of experience in the field of propulsion. He is a distinguished scientist in ISRO and director of Liquid Propulsion System Center. He will tell us about propulsion in general and liquid propulsion in particular, how it has evolved over the past many decades. Welcome, sir.
Yeah, thank you, Ganesh Pillai. Let me express my greetings to all viewers for the World Space Week 2021.
Sir, at the outset, can you give a brief overview of propulsion system used in rocketry?
Propulsion systems are power-intensive devices used for lifting off of the rocket and the rocket to cross the atmosphere and inject the spacecraft with the required velocity in the required orbit. And propulsion systems are also used in the spacecraft for orbit raising, altitude control, and station keeping. Now, when it comes to the power of the rocket engines, I would like to give you a comparison of the rocket engine power. You know that locomotive power is something in the order of around 3,200 to 3,700 horsepower is the power. Against this, the typical rocket engines used in the advanced rockets develops a power of something around 10,000 to 15,000 times of this locomotive power. Now coming to the velocity at which the rocket engines have to inject the satellite in the orbit, the velocity will be in the order of 28,000 km per hour to 37,000 km per hour is the type of velocity, what is required. Now, if you see the Maruti car speed, you know what is the type of speed? It is something around 80 km per hour. Against that, we are talking about a velocity which to be injected as 37,000 km per hour. With the available technology today, the chemical propulsion system is the only viable means of powering the rocket system. Now, the chemical propulsion system, based on the state of the propellant, it is mainly classified into two categories. One is solid propulsion system, another one is liquid propulsion system. And we have developed in the country both solid propulsion and liquid propulsion today.
Sir, Indian space program started off with solid propulsion system. So can you give a brief history of the solid propulsion system development in ISRO?
The entire space program was started in 1962. It was 1967, November 20th. We had the first successful launch of our indigenous sounding rocket, where we used 2.5 kg of solid propellant. ISRO has developed 5 generations of launch vehicles: SLV-3, ASLV, PSLV, GSLV Mark III. Now, first 2 vehicles, SLV-3 and ASLV, used all solid propulsion system. Subsequently, for the operational launch vehicles of ISRO, the GSLV, PSLV and GSLV Mark III, number of propulsion systems are developed. Number of rather solid propulsion systems are developed. And the largest solid propulsion system what ISRO has developed is for the GSLV Mark III vehicle. We call it as the S200 motor. Basically, the motor is having 207 tons of propellant loading. Now, currently, lot of new activities are taking place, new developments are taking place in the solid propulsion area. One is, you all will be knowing, we are developing a small satellite launch vehicle capable of placing 500 kg spacecraft in the required orbit. I am happy to inform that I had the opportunity to start my career in ISRO in 1984 in the solid propulsion area, and I worked in this area for 6 years before moving to liquid propulsion area in the year 1990.
Sir, liquid propulsion is considered as a niche technology domain globally. Can you please tell us how this technology evolved in India?
In fact, the liquid propulsion activity was also started in the present Vikram Sarabhai Space Center in 1969. And when the activities were growing gradually, a separate center by name, Liquid Propulsion System Center, was formed in the year 1987 with the main campus in Valyamala, where we are right now standing, and 2 units, one in Bangalore responsible for the spacecraft propulsion, and another unit in Mahendragiri near Kanyakumari responsible for testing and integrating and testing the liquid propulsion systems. And the LPSC is entrusted with the responsibility of design, development, and realization of air-storable propulsion systems, cryogenic propulsion systems, and semi-cryogenic propulsion systems for the launch vehicles. Also, chemical and electrical propulsion systems for the spacecrafts. In addition to that, we are also entrusted the responsibility of delivering the health monitoring sensors for the entire ISRO program. And really, today, you take any vehicles, liquid propulsion plays a very, very key role.
So the development of earth-storable engines, the Vikas engine and the PS4 engine, was a major breakthrough in the emergence of Liquid Propulsion System Center. Can you please throw some light on this story?
This is the PSLV vehicle, which is the workhorse of ISRO. The second stage uses 42 tons of UH-25 and N2O4 air-storable propellant combination, and the stage is powered by a very powerful Vikas engine, what you are seeing just behind. This Vikas engine is a pumped engine system developing a thrust of approximately 80 tons. And the Vikas engine is derived from the Ariane Viking engine through a technology transfer agreement. Till today, we have realized 125 of this engine. Coming to the PSLV fourth stage, again it is a liquid stage powered by two of the engines, we call it as PS4 engine. And this engine works on the pressure fed mode. And two of the sea level versions of this engine is also employed as the control system for the control purpose of the vehicle. In fact, the development of Vikas engine and the PS4 engine made a total transition in the development of launch vehicle in terms of its capability and ability to place the satellites in the required orbit.
Sir, cryogenic propulsion is a coveted technology in liquid propulsion area. The technology was denied to us by superpower nations. We toiled hard, we developed it and mastered it. Being the foremost expert of this technology in the country, we would like to hear from you this extraordinary journey.
Cryogenic propulsion system uses liquid hydrogen at minus 253 degrees centigrade and liquid oxygen at minus 183 degrees centigrade as propellant combination. Among the chemical propulsion systems, the cryogenic propulsion systems give the highest performance. Due to the extreme low temperature of propellant combination and the explosive nature of hydrogen, the cryogenic propulsion system development is extremely complex. Again, we have to produce the low temperature propellant, we have to store it with the proper insulated containers, we have to handle the propellant, and we need to develop the insulation system for the flight application. And being the non-hypercolic system, we have to develop the ignition systems. And when the hydrogen oxygen combustion takes place, it generates very high temperature, around 3500 Kelvin temperature. So we need to develop the cooling systems. And all these things makes the development very, very complex. In fact, the development of cryogenic propulsion started in ISRO during the late 80s. We started some experiments. By that time, in 1990, the GSLV Mark II vehicle was configured with a cryogenic propulsion stage as the terminal stage for injecting 2000 class satellite in the GTO. Now, considering the complexity in the development and long lead time required for the cryo propulsion development, we were looking for some support, rather the technology transfer from other spacefaring nations. And finally, it was in 1991, then USSR came forward. We signed an agreement with them. As per the agreement, they are supposed to deliver a couple of hardware for the initial flights and the realization technology associated with the cryo propulsion in India. Unfortunately, due to the geopolitical reasons, the technology transfer could not take place. And it was an excellent decision taken by ISRO management that we will develop on our own the cryogenic propulsion system. And a project was approved in the year 1995. And almost we took 19 years for the entire development. And we developed the engine system, the stage system, and we qualified. And finally, it was on 5th January 2014, we had a successful GSLV D5 flight with our own indigenously developed cryogenic upper stage, injecting the GSAT-14 satellite perfectly in the required orbit. And with this development, our country is the 6th country in the world having this guarded, high performance and highly technological intensive the cryogenic propulsion systems. What you are seeing in the backside behind us is the stage which was realized in the year 2005-2006 and put through a successful 722nd hot test. Really, it was an exciting moment when we had the first successful flight. From that till today, we had 6 successful GSLV flight with our indigenously developed cryogenic upper stage. This is the cryogenic upper stage engine developed for the GSLV Mark II vehicle. This is the Mark II vehicle. What you are seeing on the top with grey color is the cryogenic upper stage which is developed by ISRO. Now, when we wanted to improve the payload capability from 2.2 tons, we have developed the new launch vehicle, GSLV Mark III. This vehicle is capable of placing 4,000 kg in the geotransfer orbit. And the upper stage is again a new powerful cryogenic stage. The cryogenic stage has got a propellant loading of 28 tons of liquid oxygen and liquid hydrogen, powered by the CE20 cryogenic engine. This engine is developing a thrust of 20 ton for powering the stage. In fact, we have developed this engine. All subsystems were independently tested, qualified, and this is the first hardware which was realized and put through 10 hot firings. After completing this engine development test, we have tested 2 more engines and a stage, 1:1 flight stage, equivalent stage was realized, successfully tested. Then we realized the first flight C-25 stage. Even though the cryogenic propulsion technology was denied to India, today I am happy to inform the viewers that ISRO has got 2 cryogenic stages totally developed by our own people.
Sir, liquid propulsion is used for access to space as well as in-space operation. Can you throw some light on the propulsion systems developed by LPSC for the spacecrafts of ISRO?
In fact, the launch vehicles place the satellite, most of the satellites, in elliptical orbits. From there, the satellite propulsion is taking the satellite to the required orbit. Now, we develop 2 types of chemical propulsion system. One is the monopropulsion system, and second category is the bipropellant propulsion systems. In fact, using these 2 systems, we have developed number of thrusters, starting from 1 Newton thrust to 800 Newton engine. Now, what you are seeing, the second bigger engine is a liquid approach motor. In fact, 51 numbers of the LAM engine till today we have used in different spacecrafts. And this engine is also used in the very prestigious programs like Chandrayaan-1, Chandrayaan-2 orbiter. Now, what you are seeing, another engine is a 800 Newton engine, again using the bipropellant. And this engine was exclusively developed for the Chandrayaan-2. Same 5 numbers of engine we are going to use for the Chandrayaan-3 program also. In fact, if you take a spacecraft, almost 60% of the spacecraft mass is the propellant mass. And if you can improve the performance of the propulsion system, we can reduce the spacecraft mass for giving the same useful payload. So that is what we are doing now. We are developing electrical propulsion system. We have developed, in fact, till today, 3 thrusters. One is a 18 millinewton thruster, another one gives 75 millinewton thrust, third one, which is currently under development, rather in the advanced stage of development, is a 300 millinewton thruster. The whatever chemical propulsion system, whatever I told, the propellants are toxic in nature. So to overcome the problem, we are also developing green propulsion system.
We are all eagerly awaiting for the Gaganyaan program or the human spaceflight program. Can you please throw some light on the propulsion aspects of this Gaganyaan mission?
I think most of you may be knowing the GSLV Mark III vehicle is earmarked for the prestigious Gaganyaan program. But only one difference is we are going to human ride the entire vehicle. And in addition to that, over the vehicle, in place of the satellite, we are going to have the orbital module, which will have 2 units. One is a crew module in which the humans will be sitting there, and there is a service module. And for these 2 modules, we are developing new propulsion systems using bipropellant based propulsion system. And these systems are in the advanced stage of development. In fact, week before last week, we have successfully tested the service module propulsion system.
Sir, now we are talked about the new Mark III vehicle and the Gaganyaan program. Can you please enumerate the new developments, that is the new advanced propulsion systems development which are taking place in Liquid Propulsion System Center as well as in ISRO?
Today, the ISRO's capability is to place 4-ton class spacecraft in the GTO or 10-ton class spacecraft in the LEO. This is the capability of the ISRO's launch vehicles. Now, in order to improve the Mark III capability from 4-ton to 5.1-ton to GTO, we have undertaken 2 major developments. One is, in place of the core liquid stage, we are developing a semi-cryogenic propulsion system. Basically, in the semi-cryogenic propulsion system, we use liquid oxygen and rocket-grade kerosene as the propellant combination. And for powering that stage, we are developing a 200-ton LOX kerosene semi-cryogenic engine. And this engine is under advanced stage of development. The C25 cryogenic stage, which has got a propellant loading of 28 tons, powered by the 20-ton engine, also going to be improved. Basically, we are going to enhance the propellant loading from 28 ton to 32 ton, and the engine thrust also will be increased from 20 ton to 22 ton. And using these 2 improvements, the Mark III payload will be improved. And we are having further plans. Once we develop the 200-ton semi-cryo engine, we are going to cluster this engine for the future heavy lift launch vehicle program. Basically, we are thinking of clustering either 2 engines or 4 engines with a propellant loading of 400 ton. We are planning to develop a stage for the future heavy lift launch vehicle program. Most of the spacefaring nations, now they have ventured into the development of the propulsion system using liquid oxygen and methane combination. This system has got a lot of advantage because when you go to interplanetary missions, this engine will have major advantage because other planets are having lot of methane. Probably there will be a day we will be liquefying methane from other planets, and for the return journey we can use that propellant. So in ISRO, we have taken a technology demonstration program using LOX methane 20-ton capability engine And already the development is going on. Lot of hard tests are done, and our team is understanding the technology. And in future, we are planning to develop the high thrust rocket engines using LOX methane propellant combination. Now, another thing is, for recovering the stages, we need to have the engines with throttleable capability. And this area also we are working on to demonstrate the throttleable capability. Once you demonstrate that capability, we can design the system in such a way that we can recover the stages and we can reuse, which will have a lot of cost advantage. This is one area we are working. Now, in addition to that, we are also working on the tri-propellant engine system and liquid air cycle engine systems. Like that, lot of new propulsion systems, R&D activities we have initiated, and in the years to come, we may develop huge system based on these R&D activities.
So now we're coming to the conclusion of the program. Now I would request you to say a few words as a message to the viewers, especially the young minds.
As we have discussed, the propulsion system development is a key area for the space program. And the development of propulsion system involves multidisciplinary knowledge in engineering as well as science streams. When I talk about engineering, we need expertise in mechanical engineering, chemical engineering for propellant production, metallurgy engineering, manufacturing engineering, control systems, and so on. Now, the youngsters have got great opportunity to work and contribute in this area. I welcome the young minds to join in this area, contribute heavily, and take the country to a world leadership role in the area of propulsion. With this, let us conclude. Thank you, Ganesh Pillai.
Thank you.
Thank you all. Jai Hind.
Okay.